So let me quickly review what we did. We did the following morally. Actually, I really did this. Recall is that Laplacian U equals to f, and if f of x minus f of 0 is less or equals to c x to the epsilon, x to the alpha, then the following thing is true. If you put everything together, is that we found a second order polynomial p of x, so that this is less or equals to say b x to the 2 plus alpha, and this d depends on a whole bunch of things. D, first of all, is there's universal constant c star, depends on U's L infinity norm, for 1. Also depends on this guy. Also depends on this guy. Actually, let me call this f. If you put everything together, what we did, actually, we did that. And similarly, we did this also. For the same PDE, we did actually very advanced things. We proved that U minus P squared average for any R, actually, R less or equals to the same kind of equation, C D R to the 2 plus alpha, and this D is less or equals to C star. Use actually we start out with this thing plus f of 0 plus this f, but this f is not that f. Where let me call this f f2 because it's related to with f's with right hand size L2 norm, and then this also can be like a fake one. What I really used is this not necessarily to be f0. This but you can call that that is U guy. This less or equals to f2 r to the alpha. If you trace back what we did, we really did this. It's quite successful, I would say. So the estimate above, really you see U has a second order approximation in the classical norm. You can draw a picture to see it, and the second one is actually what does it mean? You should maybe you better like canceling one of that. Is more or less says that the gradient is Holder continuous. This is we prove for any r less than 1 bigger than 0. We prove this for discrete sequences, but for the r's in between, you just shake the r a little bit, then you get out r. So the geometry of this one is really easy. It's in any sense you want to say that U is second order differentiable, and the P should be the Taylor polynomial. There's no ambiguity whatsoever. But what does this mean? Actually, let me talk about this a little bit. Actually, from Poincaré inequality, you can prove even weaker one if you want. This actually figure out equals to U minus P, maybe minus another constant. This is the average of this thing. This is from this Poincaré inequality. So maybe there is A constant. This is Poincaré inequality. Let me write it here as u minus u's average squared for r. Average is less or equal to green u squared for r. And you put r here or r here, doesn't matter. Okay, that's the Poincaré inequality. You put this way, this is less or equals to this is d r to the 2. So this line really says that u is second order differentiable in H1 zero norm. And if you look at this, less or equals to that, that is the u is second order differentiable at 0 in L2 norm. And of course, if you go back to the condition, what this mean? That this condition means this is whenever f is C alpha in L2 in this sense, right? The average of f of x. Actually, you better say like the average of f. It's like that's f. Maybe you can substitute it into averages, make it even looks better. But you don't have much gain by writing the averages. And this condition and you put any constant there, they are equivalent because the averages minimizes the approximation of L2 function by constants. But really, what does that mean? So the corrective of understanding, actually I already said it. You better look at horizontal is the x, the vertically is the H1 semi-norm. Then you see really they are continuous. However, the one way, as we did, is that differentiable in H1 0 or L2, etc. Or this kind of pictures. We look at H1 semi-norm, then they are really differentiable. So this norm totally lives on our mind. I mean, how do you see a function in H1 0? It really is not that easy to see. For example, even in the L2 norm, it's what does it mean? Right? What's that mean? So whenever you prove a theorem, the first you have to think the theorem really on the face value. It's on the face value whatever it means. So let's examine it more carefully. So even let's think about really easiest the question, f minus f bar for r squared average. Say let me normalize it, right? What does that really mean? If I take this equals 1, right? What does that really mean? Right? What is this? Because we really did it. Under this condition, we proved u is like second order differentiable. Actually, that's not an easy question. Even say take r equals 1. So what is that? Even say it's equals 1. What's that mean? Actually, if you think about it, which I will the more things I will talk about it like a Friday or Thursday. We spend a lot of time to define the L2 space, then say they are integrable. But we didn't think about this, what does it really mean for a while. But if you ask a physicist, what do they do? Whenever they see something integration equals 1, they say, that's a probability density. Then they move on. And use this idea, they actually invented quantum mechanics. And the ideas of quantum mechanics is quite successful. And it is how they discover quantum mechanics is not they first thought about probability. Maybe they discover probability first, but actually maybe they look at something's integral equals constant, then y is equals constant, then it always equals 1. They say, that's probability density. Then they think about intuitively, physically, and everything why it is 1. What's the probability density means? Actually, the correct way of understanding this integration equals 1 should be kind of probability density. So this is very much related with quantum mechanics. Quantum mechanics. So physically, you won't be able to see what's the difference between this number and this function and his average. You only know that the difference between this and a number's difference totally equals 1. So what do you see is actually this kind of pictures. So you know there's a special value. Actually, this value is not that important. It's like it has to be that number. Then here is like a ball one here. Then here's a level here. Then the function changes a lot. I mean, I guarantee you, our theorem really implies this. On the face value, it says that no matter how the value go up or down, far away or close, no matter what, whenever this thing is true, we have consequences, right? So saying a function satisfies this doesn't mean it is continuous in any way. It just means that when the function, when the value goes to 0, the variant, the thing go away from this average, getting smaller and smaller. Right? That's what this actually means. I mean, you can easily make up a counter example, right? You have a spikes, always jumping really fast, really far away, but still making that goes to 0, right? You can easily do that. And guess what? Our theorem still applies for those kind of crazy f. Right? It's no kidding. We really did it. So you see those whenever I see those kind of things jumping up and down, I would say that they are quantum effects. You have a small, but when you shrink the ball with smaller, those kind of small probability jumping from what it should be, the probability getting smaller. Only infinitesimally, the probability will hit 0. But those small things will be there. And you can make up counter examples. It really happens. And that's really what we did. It's pretty strong, but you do see this quantum effects. And you cannot go any stronger than what you proved. So that's the first comment I want to make. The second comment is that first there's some quantum effects we see. The second comment I want to make is that the same method, the same method that yields like a C1 alpha, say C3 alpha, C alpha estimate. Because what we did is that we emphasize on this second order approximation, which is totally personal, right? Why you want second order? You can use like linear approximation. I mean, nobody can stop you doing that. So if you, for example, let me state a theorem of linear approximation. So the following thing is true: if Laplacian U equals to F in ball 1, then their linear function L, say right. So then we can prove that U of X minus linear function of X less or equals to D X to the 1 plus alpha, provided the F behaves properly in L infinity. For example, I mean I can do other norms, but one way to do it is this: F's L infinity norm is less or equals to, this will be X ball R to the minus 1 plus alpha times a constant. You kind of you can make this constant. You have minus 1 there, but you can see this minus 1 plus alpha is always true because this is negative constant. In other words, if F is bounded, this is always true by running over the statement. If right hand side is in L2, this slash, say you can do this. Provided this F squared average, you don't have to take an average anymore. Less or equals to F R to the minus 1 plus alpha. If this is true for any R, then this is true for any R. Right, and you can this actually you can use let me do the computation. If F is in some LP, that is really correct. Say what is that? You don't have the minus constant in this case. So what is that? For example, this less or equals to, say, F to the P average. P, right? For any P bigger or equals to 2, and this is a Schwarz inequality. Then this equals to F to the P bar R 1 over R to the N over P, right? Right, this is exact constant. So in other words, I can write it R to the minus N over P, or I only need this constant to be that constant. What is that? You see alpha equals 1 minus N over P. So in other words, if right hand side the function is in LP for this P, and you will be C1 alpha for that alpha. And I'm sure if you learn the elliptic equation, you have seen this kind of estimates one way or the other. because you can also see it from software embedding. So you have a C1 alpha, and you can also so this is positive if and only if P is bigger than N. So if P is bigger than N, you have C1 alpha theory. Actually, the same computation, a similar computation, you can show that if F in LP for P bigger than N over 2, you'll be Holder continuous. I won't do that computation. So this remark, and another remark is that like a general philosophy is the following, that what we really did, the proofs based on two facts. One is limiting equation. What do we mean by limiting equation is that you let the errors and the scales all goes to 0. So in this case, you just let f equals to 0. That's the limiting equation. Has smoothness. Namely that U is smooth. Actually, when you prove like C2 alpha, you need U to be C3. C1 alpha, you need U to be C2, and etc. etc. You can push that a little bit more. And second is approximation. Namely, solution of this can be approximated by a solution of that. Right? This and any kind of approximation of this and smooth of that implies this precise shelter estimate. Then you look at it again. So the perturbation, what we did is really perturb everything. What we did is we perturb the 0. Right? So we perturb 0 by first we perturb by constant, then perturb by a function. However, like the same thing, clearly you can do this kind of things. It can be if you look at Laplacian U equals to 0, the perturbation don't have to be right hand side. You can perturb a lot of things. For example, how about this? I mean, let me even make it more general. If I want, I can write a really very, very general equation. Right? So what is this guy's limiting equation? One easy way to do it is you look at the blow-ups. Then let R goes to 0. That's the blow-ups limit. Let me save a little bit of time. And if you look at this function, you will see this. Equals to R squared. Right? You see a lot of R's. You let R goes to 0. You see that all the things like law of the terms right hand side, they all disappear. Then what is this? This is morally Laplacian. this like limit after change of variable. Provided Aij, of course, is positive definite matrix, right? If Aij is positive definite matrix, it's a constant, you can always change it, that equation, into Laplacian. So it's really good. The Leibniz equation is harmonic. At least it enjoys all the estimates of harmonic functions. Then this is good. Then whether you ask the next question, whether you have approximation, right? Then clearly you do. Is you can do this energy estimate.
So this is the only for the Holder equivalence, because you are assuming the n is sufficiently small.
Yeah. It's Holder, right. It's so approximation. You can really do it. One way to do it, like let me name the operator L of U. Let me only compute one of those terms. Say B of X, BIU. So this term Aij, and this Ij. If you say a minus sign, you might minus U, provided say U on the boundary equals to 0. This would be Aij partial Iu partial 0, which is morally like U's H1 0 norm squared. Really, really nice. So that's what we want. And this kind of terms, you can handle easily. For example, you can do this. This you cannot do much. This goes to here. That you can do solar embedding, for example. Then this has to be linear. It's 2n over n minus 2. And this is, let me do it half. Then the exponent, they also be added 1. So we hit everything here. So this is half. This will be a 1 over n. So inside is n. Right. So this list all equals to U's H1 0 squared B's I. So in the case this is small. This is really small term. And you can always make that term small. For example, you do this kind of estimate. Let me do one more remark. If you compute this n norm dx in for 1, it's like a miracle. It's exactly equals to by changing variable there, it's really equal. Then this, of course, goes to 0. This is by the integrability of if B is in Ln, then that's the case. And if B is not in Ln, this open problem, nobody knows how to do it. And if you compute the C term, C would be, you need to be in Ln over 2. And can you do better? Nobody knows. If you can do better, you solve Navier-Stokes problem. It's this everything. You do the silliest computation, you already do the cutting edge technology. So now, remark 3 is what we did is pointwise regularity. Sometimes with classical, meaning that you can do it, you can see the regularity by naked eye. Sometimes quantum mechanical, namely that you can do it by the L2 norms one way or the other. And you see some quantum effects, but kind of you believe it. So this is pointwise. So how do you pointwise to local? In terms of the pointwise, really, the ultimate estimate is the estimate in the strongest form, and you can easily do this theorem. So f Laplacian u equals f. I mean, I can state like a AIJs if I want, but you know, let me stick to Laplacian. With f, say, holder in ball 1, defined as semi-norm as is f. I mean, I can define it this way, right? It's semi-norm. Then u is c to alpha. Really is that u is classically d squared u exists, and really in the classical fashion, as classical as possible. Everything's okay. This is really This is what we did before was at the origin. Here I want to say that you can really see the classical picture. So how can you do that? It's easy. What you do is you even what we did was origin, but the origin can be anywhere. You are the king of yourself, or queen of yourself. Wherever you're standing is origin. So you apply the estimate at any point in half ball. You get the approximation, right? So you get u of x minus the p with index y, x less or equals x minus y to the 2 plus alpha is a c. This you can make it really universal under normalization conditions for all x and y. Say less or equals half. Y is equal, right? It's like you write it down. You see this is true. The thing is, you want to show that why this is second out. Why this is, you can take a derivative, then you can take a derivative again. It's actually from this easiest fact. Let us say a lemma. This is clearly true. Say gradient of p, gradient square p. Actually, let me just say this. Later I can see 0 p's L infinity. This can be L infinity. That's only a number. If p is the second order, if p second order. The easiest proof is P is a finite dimensional. All the norms are equivalent, and this is clearly true. So right hand side is a norm, left hand side is semi-norm. Semi-norm is always less or equals norm. Done. But but the real power is the scaling. This is equivalent to say that if you look at the ball R, then the correct scaling is this one. I mean, these two clearly equivalent. Do you believe that? I mean, this is mathematically equivalent. Second line, you can let R equals 1. Then you can prove from first one to second one by scaling. We did so many times. Let me skip it. Then I say this is true. So morally, of course, whenever you do this, any polynomial you can write it in correct way. For example, you can write it like a plus a1 x minus y, right? I mean, the center of attention for this one is y. So you can always write it in this way. Right? This is just by shuffling the coefficient. And of course, this would be the first order derivative. Actually, by definition of calculus, this term is already defined. This has to be the derivative of u at y, right? Because this what's the definition of second order derivative? This is u minus linear function. If you can write like a little o of the distance, that has to be a derivative. So this, no matter what, this thing should be differentiable. We already know that this is at y. This maybe we don't know that yet, but morally we think that's the second order derivative. But for example, I won't have all the time. So how to see this one is like behave good? But that's easy to do. So just you have this, you have that everywhere. Like okay, now you draw this ball. Here's ball 1. Pick any 2 points, right? And suppose the distance is r, right? And this estimate is true in any r. So for example, I draw this ball, I draw that ball. I have all kinds of estimates like that, right? In ball 1, u minus a polynomial has correct error. In the second ball, u minus another polynomial has the error. And the error, if I take the radius all comparable with r, then I have u minus p1 less or equals r2 plus r alpha u minus p2. In that ball, this less or equals to r to the 2 plus alpha. I skip the constant. Then of course, in the say center of the, I draw about that there. I get p1 minus p2 in this maybe 2 of 2 1 plus alpha, right? But you get correct order. Now I apply this statement. Once the polynomials area infinity norm is r2 plus alpha, then the first order derivative times r is r to the 2 plus alpha. You see? Then not only that, I have, for example, here I have r squared. This guy taking d2 derivative is second order derivative there, and this one is there. So I have a d squared u. Morally, I see that like x1 minus d squared u x2, right? Less or equals to 2 times r to the 2 plus alpha. For any x1, x2 has distance r. Then what I say is coefficient varies with respect to r as Holder continuous function, exactly coefficient r. And you can play other coefficient if you want. So
you're assuming that you see 2?
No, actually prove that you see two are kind of this. I mean, not. I really didn't prove it, but this coefficient really correct. You see, and actually this line. If you look at this line, this actually means that if you thinking this as a function, is differentiable, and the coefficient should be this, and everything is, if you use this in a tricky way, you get everything you want, because R is arbitrary. It's true for any x and y. Okay, so this you get local estimate, and the thing is really easy to do. Then the other thing, the L2 to H1 zero theory, you can do the same thing. And in that theory, actually something dramatic happens. Let me state one statement. Is this? Is that first look at the f. Okay. Then let me assume f is Holder continuous in the L2 sense everywhere. What that mean is f minus f bar in ball R of x average in ball R of x, take a square root, I normalize by the correct error, then I assume I take suit in R less than 1, bigger than 0, x in ball 1. But there's one thing is that this sometimes may go out of ball 1, right? It's like I want to say f is always has this kind of error. What I do is I look at unit ball. I pick any point, then I draw the balls. But if I reach ball 1, this unavoidably go out. So let me be conservative. Make sure this never go out. Right? Otherwise it's like this is. Otherwise it's not defined. So if this number is finite, you should believe that this exactly says U is Holder continuous in L2 fashion in the correct way at each point, at each scale in ball 1, right? And in the L2 sense, in each point you see this quantum effect, right? If that number is finite, guess what? There's a theorem proved in the 60s. These two numbers are equivalent. Up to measure 0 set. This amazing theorem. And on the left hand side it says that f can be approximated in each scale, each point by constants, like a Holder continuous way. On the right hand side it exactly says that it's classically Holder continuous, no quantum effects whatsoever. Right? It's right hand is a totally classical picture. The left hand side is quantum picture in each scale. But if you can see the quantum mechanically, every scale, every point, you don't have quantum effect at all. And the proof is actually easy. The thing is like, if this is finite, what do you see is at each point, say, origin. You might have like if you look at each individual point, you might have like really quantum effects going up. But you want to show that it cannot go up actually. If it goes up, like small probability, then by Lebesgue lemma, it's it has to go up like really with respect to positive measure. Then that's impossible because what it says is you approximate by a constant in all scales. So even in there, you can be approximated by that constant. Then if you're standing here, then you can be approximated by similar constant even in a bigger scale. So you can expand that constant to a bigger scale. That violates that small probability. That's basically the proof, actually proved by contradiction. And another thing, if you still bothersome, one easiest thing you can actually prove, if say this is the first thing you want to prove is actually following. If this is finite, then you can easily prove, as what we did in the proof of Schroeder theory, actually, that if you can be approximated by a constant and the error improves, then those constants will be forced to converge. The strong convergence forces these constants behave reasonably. If this wobbles wildly, that cannot be true. So first thing, you prove this thing at any x, they have to converge to something. And by Lebesgue differentiation theorem, this has to be x almost everywhere. And the error is comparable with that. That's the first thing. It's like once you have very strong convergence of the errors, then the May player cannot play a trick on you. So once that is true, then you see this kind of picture. If you in a smaller scale you see the function goes to a very tiny picture, then you can enlarge the scale wherever you want. You will be approximated by almost the same constant. That's basically says that this quantum effect is impossible. So also not only you can prove this, you can also prove up to the boundary. So for that, the only thing you want to prove is that if the limiting equation, and of course you want the limiting domain also. So what's the limiting domain for a smooth manifold? Of course, tangent manifold. Right? What the tangent is? So limiting equation in this case is actually this equation most of the time. So the only thing you want to make an observation is any solution of this is smooth, and everybody knows how to do that. It's you just do odd reflection. It's harmonic. Then it is smooth. Okay, so smoothness is clear. So I have 10 minutes. Then what else I want to say? So basically, what I say is that limiting equation is nice, and you have approximation. That approximation can be anything. I mean, I did one like energy estimate. For PDE, sometimes you have all kinds of other estimates. You know, it's for say force order equation and other kind of elliptic equations. You all have those kinds of estimates. Then you iterate that, you get this precise Schroeder type estimate. really talk about something not so elliptic. So how about parabolic? So Thursday I will talk about more like the integral estimates, and for parabolic equations it's like you can many things you can do the same thing. Say this is this type of equations. Then first of all the scaling. In order for this main part to be invariant, you better talk about scaling in x and the time scales differently. If you call this h of u, then h of u r equals to r squared f rx r squared t. If let r goes to 0, you really see that. So you this is the correct scale, the correct scaling. So now pretty much you can do everything. For example, maximum principle. Here the boundary should be physical boundary. You define parabolic cube is ball one. There are several different ways of proving it. For some reason, I like this. This actual scale of that parabolic scale. You better define parabolic scaling. Parabolic scaling of a set is Rx r squared t. Lx t is equal. So this would be equal to R. Parabolic scaling of Q1. Really, the algebra, really nice. Then if heat equation equals say F in Q1, with that U say equals to 0 on this parabolic boundary. Because if you think about heat diffusion, you can physically you can control the initial temperature and the temperature on the boundary. All the other temperature is controlled by nature. You cannot say much. So here is the initial. That's that. So boundary of that is defined as boundary ball 1 cross -1 0 union ball 1 cross this -1. Should I say that? Yeah. That's the parabolic cylinder. Then you have the maximum CFs. Everything. Exactly as before. I think this case you can take C actually equals 1. And the proof is you just compare U with the proof. Compare U to like a T times, in this case a T plus 1 times anything. So you see this if boundary value 0 and you kind of want to go up by the heat source, then I say no heat source can beat this thing, and this is the boundary temperature is really positive. This linear function in T, and if you look at this, then heat equation H actually equals to F L infinity. H is bigger or equals to U on this parabolic boundary. So U will be bigger or equals to that. Then you apply the maximum principle. Then then also this will imply that the same computation actually shows that use derivative would be bounded, because once you have maximum principle, you can do a lot of things. Then this, at the same time, this gives you both regularity and the approximation lemma. This is F controls the U, right? This is the perturbation argument. Is U compared with 0. This is the error. The only thing I want to say is that in second order case, what is second order polynomial? And you do exactly the same thing, but the only thing here is that second order parabolic polynomial. What are they? Because those scaling should be goes with that. So the parabolic, all the second order parabolic polynomial is actually only including those things. Will be a times t plus half of x transpose b x plus c times x plus t. No, say t times x, t squared times. Why? Because if you do a parabolic scaling, this is third order, that's fourth order. You change your t to by r squared of t. Right? So once you state the theorem this way, everything you can do it line by line from elliptic to parabolic. You have second order polynomial approximation, and the harmonic will convert it to this plug-in heat equation is satisfied. The harmonic compare with this h of this polynomial equals to 0. That's the same thing as to say a equals to trace of b. That's the correspondence. Then another thing is a kind of funny thing, because I just 2 minutes I have to be say something interesting. In 2 minutes is that like for Laplacian, the boundary for omega converted to planes with this kind of scale, right? And if you look at the omega in Rn plus 1, then you do this kind of scaling, xt to rx r squared of t. Now, what is the picture? It's actually you get something really interesting. Is that the smooth object? What do you mean the limiting domain? The limiting domain has two properties. First is smooth. Second one, if you do a scaling like that, it's invariant. Right? It's scaling invariant domain. Then the tangent is a smooth object such that you do this kind of scaling is invariant. Tangent plane of boundary of omega is scaling invariant. And I would say smooth also, otherwise no. If you add those two conditions, guess what? You only observe two pictures. This is something new. One is this implies tangent equals to vertical things, namely that a times a vector equals to 0. This is like a for a is not. Here, this is like typical lateral tangent plane. You see this is Q1. If you standing here, you pull it up, you will see this thing. That's the invariant tangent plane. And there's another class is this kind of things. Is this also invariant? For any M matrix. You do scaling. This is invariant. So for cylinder you won't see this, but for general parabolic domain, you standing here, if you blew it up, you see a parabola. Here you see this kind of parabola. It's starting to be invariant. So for this one, you do have new theorems, like the regularity theory actually depends on this matrix M. And for different M's, the regularity theory might be different. And there's a paper by Nirenberg and Joseph Kuhn in 1960s, and there's also, I wrote a paper in I forget, maybe 94. You do observe that, say, when this M is, the trace is, say, positive definite, then you have a regularity in any space. And there are sequence of discrete matrices, negative definite, then you cannot have regularities up to certain order. You do see a phenomenon like that, even for the simplest parabolic equation. So okay, let me stop.